In this video, I'm going to show how to solve the diffusion equation using a very simple method, the Euler forward explicit discretization. Now, this is very simple. I'm going to also show how to visualize the results. And more important, I'm going to show how to build a code that I can use later for more complicated problems. So this is the equation. This is the diffusion equation, and in particular I can use periodic boundary conditions or Dirichlet boundary conditions. Now the discretization that I'm going to use for the second order derivative is this one here. If I have time at the end of the video, I'm going to show how to obtain this expression. It's not complicated, it's a Taylor expansion. Now the matrix representation of this operation is here. So in particular, I am showing here the matrix for the Laplacian with periodic boundary conditions. So if you see, this thing here is basically the same that is written as is here. So we have the main diagonal is a -2, and then on each side we are going to have a +1 and +1 on the other side. Now, I can write the full discretization for this diffusion equation. I'm going to show here. So on the left hand side we have the derivative, so it's basically just the difference between the previous time step and the current time step, and on the right hand side we have the expression for the second order derivative that I just wrote previously here. So we have the contribution of the center is multiplied by -2, and then on each side we have the contribution of the previous cell and the next cell. So it's the same that is written here. Now the most important part to notice here is this thing. This derivative is evaluated at the present time step, all terms here. This is the most important part to notice here. And what I'm going to do now is I'm going to solve for the solution at the next time step. And to do that, what I do first is just multiply both sides for delta t, and then I'm going to add u, I, n on both sides, and I'm going to get this expression here. Now, this expression is for any cell on the domain, right? I1, I2, etc. So I can use another array. I'm going to call it capital U, which contains all elements on the domain. So we have this capital U contains U sub 0, U sub 1, U sub 2, etc. And if I do that, notice that I can also use the same variable here, capital U here. So this matrix A here, what it does is it represents this operator here. All right. So this operator is A acting on capital U. And if I do that, then I can factorize the capital U outside, and then I am left with this identity matrix here and this factor that appears here. So this is the expression that I'm going to solve. Now, two things to notice here. The first one is that this expression in parentheses is constant. It doesn't change in time. So I'm going to assign this to another variable, and then I can put this into a loop. Okay. So for instance, if I start from a initial condition U0, then for multiplying by this factor, I'm going to obtain U1, and then the U1 I plug it here, and then I'm going to get U2 and so on. So what I'm going to do is write a loop for this expression. And another thing to make a comment here is the following. This is Euler forward discretization. This scheme is very simple to implement, but it's not stable. The solution is going to blow up. And if I want to make this useful, I need to use a really small time step. And this is the stability condition. So the time step that I need is really small. I need to use a very small grid spacing to to make this scheme stable. Later on, probably in another video, I'm going to show where this expression comes from. But for now, I'm going to show the code, and I'm going to do it step by step, all by scratch, to show all the details. Now, my purpose in this video is, of course, showing how to solve the diffusion equation, but more important, I want to show how to build code that I can use later on more complicated problems. So I'm going to try to write a code as modular as I can, okay, so that I can reuse in the future. So I'm going to start the first thing I'm going to do is to choose a initial condition. I'm going to choose this one, Gaussian bump. So this B is the center of the distribution, A is the amplitude, and C is the width. So I'm going to plot this function. So first I'm just going to import the NumPy and Matplotlib for plotting. PLT, alright, so I have my function here, exponential minus x squared to c squared, and parameters, then the domain, I'm going to use equal to 2 so that the domain goes from -1 to 1 and with some spacing. Okay, now plot this thing. Open a figure. X and Y, and show the figure. So this should work, let's see. Okay. Now I'm going to use my diffusion equation to advance this initial condition. So we need to write a function to advance this thing. I'm going to call it diffusion solver. Euler. And it's going to have some parameters. So for this, what I need to write my this expression here. So it's identity plus this delta TD divided by h squared A. So I'm going to write sparse I. So I need library for sparse functions. Sparse, okay. And this is going to have some size plus delta TD divided by h squared dt delta x squared, and this is going to be multiplied by some matrix A. So this matrix A is this thing here for the case of periodic boundary conditions. I'm going to call this thing here M. So notice that this matrix is constant. It doesn't change with time. So I'm going to multiply this thing for my initial condition, U0, and then I'm going to get U1. Then the result, I'm going to plug it here as U1, and then I'm going to get U2, and so on. But this thing remains constant, so I'm going to write a loop for this expression here. So I'm going to call this M, and then I write my loop for all index in the range of the time steps I'm going to do that operation. So it's M dot U, and the result is going to be the new value of U, and I'm going to return this thing at the end. I think that's it. Let's write the parameters here. We need the D. Also in steps, just a few, just to see if it works. And this N here is we have already the domain, so I'm just going to compute the length of the domain X. So we need this X as parameter. We are also going to need the initial condition and the time step and the spacing and the diffusion constant. What else? So we need, of course, to compute this matrix. This is going to be a Laplacian. It's size and spacing. So this matrix A is this matrix here. I'm going to use another function to compute this matrix. So let's see. I need my initial condition. So initial condition is going to be the initial condition, but I need to copy the content of that. So what this does is copy the content, type, and length of U0 into U, and then I'm going to use that thing as initial condition. Let's see if there's any mistake. I think that looks okay. I need the steps. Now let's write this function here. So I'm going to, for this I'm going to use a sparse diagonal. So I need to write what? SP diagonals, yes, this one here. And for this I'm going to need the data, the locations of the diagonals, and the size. So the data is these three diagonals there. So one at the center is a -2 multiplied by ones, and one above is an array of ones, and one before is an array of ones. Okay, so I'm going to do that. I'm going to write first center. So it's -2 for an array of ones. I'm going to write that later. The next diagonal is E. One before is E. I need to write this between square parentheses. Now the location. The location is center is 0, and 1 before is -1, and then 1 after is +1. So -1, 0, and 1. And finally, I need the size n by m. And now I have to write my array of 1. So this is going to be, what is np 1s of size m. That should be it. I'm going to call this thing A, and then I'm going to return what? So this matrix A divided by h squared. So this is 1 by h squared. In this case, I'm calling it dx. Then multiply by this A. So this thing here, A divided by h squared, is the Laplacian. So instead of A, I'm going to call it L. This is L. And then I don't need to divide by h squared anymore. I'm just going to remove this part here. I don't need the parentheses. Okay, looks okay. Let's see. I need now the periodic boundary conditions. So I'm going to use periodic boundary conditions. So this is easy. So the first column, last row is a 1. First column, last. This is 1. And the other one is the opposite, so this should be capital A. So this is last column, first row. So -1, 0. So those are my periodic boundary conditions. And the Laplacian is called here, then goes there. So this A divided by delta x squared is this Laplacian L. And then in the loop I multiply by u, and u is going to have as initial condition the content of u0. I think it's okay. So let's try to see if this works. I'm going to copy all these things there. So this u0 is this initial condition, and what I get from this is the new value of u. Okay, and this is what I'm going to plot. So let's see if this works. I'm going to run it. There is a mistake here. 23, 14. Probably the mistake is because here I'm using a sparse format, and then I'm trying to do element-wise operations. So I need to change the format here. This changes to a normal format. Then I do my element-wise operation. And when I finish, I am going to change it back to a sparse format. This is compact sparse row or something like that. So let's see if it works. Okay, looks like it's working. Let me check once again if I wrote everything correct here. Yeah, I think it's fine. Yeah, it's working fine. So now I'm going to plot both things, okay? So this is the initial condition, u0, and then the result. Let's plot both things. Okay, it works. I'm going to write some labels. So this thing is going to be the initial. And this thing here is going to be the last result after a number of time steps. This is after steps. Okay. So this is a number, so I need to write a type here, floating type. Let's see. I think I need, this is a string. Okay. Label. Okay. So now it works. So let's try to make this thing better. So the first thing I'm going to do is I'm going to write this thing into a function. Initial condition. It's going to have some parameters, and it's going to be this thing. So it's going to return this thing. Return that thing. So I need the domain, and what is the value of the width, and I think that's it. So now this u is going to come from the initial condition function. And just to make this thing a little bit better, I'm going to write everything here into a main. Main function, and then run that function. Let's see if this thing works. Yes, it's working fine. So let me add some labels for the axis. So PLT X label. This is X. Then PLT Y label. u are at all values in x, and because we are plotting two different times, so this is also a function of time, and that's it. Let's see. Okay. Label. Label. Okay. X and Y. Now, as I said before, one of my goals is to show how to write this in a more modular way. And the reason is because sometimes we need to use a function that I wrote in another code. So I just want to use that function. And for that, we need to add another line. I'm going to add here, if name equal to main. Then run this thing. I'm going to explain how this works in a bit. So let's say we are already doing another thing, and I want to use the function that is in this code. So let's say I want to plot the function again. Okay, so I'm just going to copy this thing here, and then the same code for plotting. Let's say this thing here. Okay, only the initial condition. Only the initial condition. So we don't need time steps and any of those things. So probably I don't want to write this and that. So let's say this is for -1 to 1. Then the spacing 0.005. 0. I'm going to load this function. Okay, import from this code diffusion 1D. Okay. Some short name foo. All right. So now this function comes from foo. I don't need the indentation. Okay. So let's see if this thing works. So notice that I am not writing the function for initial condition. I am loading this function from another code from here. That's what I'm doing. So I'm going to see if this works. Yeah, it works. So what happened if I don't use the line, the if name equal to main? If I don't use that line, just going to comment out. What is going to happen is that it's going to run the entire code and my function, my initial condition. See, it runs the entire solution and then my initial condition. But that's not what I want. I only want one function here, so that's why I need to add this line there so that it doesn't run everything, only what I want. But Okay, let's do it one more time. Okay, so this is why I need to add that line, so that I can reuse some function that I am using before. Okay, let's try to continue doing this thing. I think I finished. I already wrote a function for the initial condition. We can use a different initial condition. Let's try another one. For instance, let's try a step function. For a step, I'm going to use a Boolean expression for to define the function. So I'm going to use a np where, and this where is very simple. What it does is let define some constant, for instance the absolute value of x, and if this thing is less than some width, less or equal some width, then it will take this value, and it's going to be 0 otherwise. So that's what it does. So I'm going to need the value of that width as parameter, and it's going to return this thing. So let's see if it works. What is the mistake there? Let's see, return np where, of course I need a np for there, okay. I need to define the width. Initial condition, width. And the width, for instance, some value like that. Let's see if it works. Okay, now it works, but I mean this initial condition is very difficult because of the ages, and we are using a explicit scheme, so this is not very good. But what we can do for the moment is make the time step much smaller to see if we can at least see the initial condition. Yeah, I think now it works. I'm going to plot a little bit longer. Okay, so that's my initial condition, and then the result. Finally, just to make this a little bit better, I'm going to make a switch here. So let's say if kind is equal to Gaussian, then do that. Else, if the kind is step, then do the other thing, and we need to add a default. So is everything else, then I'm going to return just zeros. Zeros with the same size as the array. This is an np zeros. I'm going to use 0 like. So this gives me the same size and type as the array x. And I think we have it already. see if it works. Initial condition, kind, okay, equal to Gaussian. It seems that I need to, yes, because this is a string, these are numbers, so there is some problem here, but I can just write the specific value. 0.2. Okay, so I don't need this thing anymore. Which one? With, yeah. Okay, let's see if it works. Yeah, so that's Gaussian. I can change here to step. Okay, and if I do anything different, it's going to give me just zeros. All right, so that's it. So I think I'm going to stop here for a moment. And so what we did so far is to write a modular code so that we can use it later in the future, where we can add some more complex implementation. And this is very important here, this line here. It will allow me to use this code in the future just by calling the code as a external library. All right, so I'm going to continue a little later. What I want to do next is to show how to implement a semi-implicit discretization. And what semi-implicit discretization does is to allow me to run the solution for longer time. So this one, the one that we did using the Euler discretization, this one is okay when the time step is small or at early stage of the simulation. I'm going to run it. So this looks okay. However, if I go a little bit later, it's going to start to become unstable. See? So if we want to continue using Euler, so one thing we can do is do a small time step. But what we ideally want is to have a scheme that is unconditionally stable, and that is what the semi-implicit discretization is going to do. I'm going to show how to do this. So this is the diffusion equation, and this is the discretization that we are going to use. So this is very similar to what we did with Euler, except that in Euler, this the second order derivative is evaluated at the present time step, and in a semi-implicit discretization is evaluated at the next time step. That's the only change. Now, if you see, we have you evaluated at the next time step on both sides of the equation. So I'm going to move everything on one side. All this term containing n plus 1, I'm going to move all of them to the left-hand side, like here. And then I'm going to use the same trick that I did before. I'm going to call this expression here is A multiplied by this array. This array contains contains the values of the U for use at all cells on the domain, U0, U1, U2, etc. And now this expression looks very similar to the one that we got with the Euler scheme, except for by this sign here. So see, here is positive. In this expression is going to be, there is going to be a minus sign. And then the only thing we need to do here is to compute the inverse of this expression. And then we are going to have the solution for the U variable at the next time step. So computing this inverse matrix can be a little complicated. So what we do in Python is we are going to solve directly this linear problem. So I'm going to show how to do that. I'm going back to my original size of the time step here. So I'm going to copy the function for the diffusion solver. I'm going to modify that one. This is going to be only diffusion solver, and I believe it has the same parameters. Let's see, this matrix is the same except for the sign. I'm going to do this thing here. Okay, so we have now a minus there, and now what we have here is a linear problem. So let me show you. This is a linear problem. This is ax equal to b. Okay. And we are going to use a function called spsolve. So spsolve is in the linear algebra package. linalg as LA. Now, instead of doing this multiplication here, I'm going to just comment this part. Instead of doing that, the solution is going to be what we get from the solution of the linear problem. U. Okay. So just to comment again, what this does is get you the solution of the linear problem. So in particular, the linear problem here, A is U at the next time step M equal to U at the present time step. That's the linear problem that I'm going to solve, and that I think that's it. We can try to run this to see if it works. I'm going to delete this part. We don't need it anymore. So let's run this thing to see if it works. Instead of diffusion solver Euler, I'm going to call now only diffusion solver. Seems that it works, but now it should be stable, and what that means is that now I am able to use larger time steps, as you can see here. Previously, for the same size of the time step, I couldn't use this small time, this big time step. Just to check again. No, not this. It's here. Okay. See, and it gets worse as we go on. So, for instance, for 100, there is nothing. There is the solution is already super big. See, 10 to the 200. All right. So, if I use my semi-implicit scheme, this should be okay. Let's see. Okay, so now it's working fine because we are using a scheme that is unconditionally stable. I think with this I conclude this part. I'm going to show just a brief summary of what we did, and later I'm going to show how to write expression for the second order derivative and some other things.